Hello, everybody. This is Professor Ma, and this is the introductions to the PowerPoints on English functions. And we're going to talk about the notion of inverse functions and some basic algebraic examples, and a little bit about the graphs of inverse pairs of functions. Okay. We'll start with the definition of a function. The definition of a function is that for any it's a machines, but we put input into the machines, the machine going to produce one output. That's a definitive output. Okay, and that's the important point about functions. And on the pictures, we usually draw like that. X produce one f of x. One arrow goes out, indicating the function evaluates it or produce the output. And one of the things of course we would like to do is be able to reverse the procedure. That is, so I tell you what the output is. Can you tell me what the x that it came from? Well, this procedure of associating the output, I tell you what the output, you tell me what the input that came from, might not be a function. Okay, in other words, there might be multiple answers where the x came from x that gives the y. You don't know which particular one. So it might not be a function. Here's something. So if it is a function, we call that procedure the reverse or the inverse procedure. We'll call that f. We put a little, unfortunately, like exponent notation. We put a little -1 on top. It doesn't mean, first of all, this -1. Do not confuse this as 1 divided by f of x. Okay. And if you want to f of y, if you want to do something like that, we rather like that, meaning reverse the reciprocal of the entire formula. But here, -1 means the inverse procedure, if it exists. Okay? It tells you, you say why the output is, then this procedure will tell you precisely which x it comes from. Okay? And just because these precisions, that prevents the procedure, a lot of procedure to be functions. Like what? Okay, here's one that has an inverse. If I take a number x and the output is twice of that number, and then if I say the answer output is 2, then you know it came from 1. 1 times 2 gives you 2. You just half it. 1/2 of 2. If I tell the answer is 4, output is 4, then you know it came from x equal to 2, etc., etc. Okay, so I can reverse this procedure and divide it by 2. So this is the reverse procedure. You take the output y divided by 2. That will give you the x, where it came from. Okay. But on the other hand, okay, f of x equal to x squared, I don't have the luxury of knowing which x it came from. Suppose I tell you y is 9, the output is 9. I know that 2 numbers came from. I mean, x could be 3, x could be -3. I know the reverse procedure produced 2 possible x's. It's not a function. Okay, so if I tell you 9, we don't have the precise numbers, what is +3 or -3. Hence, here's a function, and because of multiple x hits the same number y, hence when I reverse it, it goes to multiple inputs, so hence the reverse procedure is not a function. On the graph, basically we're saying, okay, here's a graph on y to x squared. Locating y to 9, I'm asking where does x came from? Well, there are a couple of x's came from -3 and 3. I don't know which one it is. So therefore, this reverse is not a function. Okay, but we'll notice, however, if I restrict it later on, that I can turn this into kind of into small pieces of functions. inverse has an inverse function. So when does the inverse function exist? Inverse functions exist when the function is said to be 1 to 1. Okay. What's 1 to 1? A 1 to 1 function is a formula that if you put different x's into the formula, it will produce different number y's comes out. Or one input produces one different output, another input produces another different output. So you don't have the case where you have the same pair of x's wind up with the same 9 and the same answers. Okay, so 1 to 1 function is 1 to 1 if that doesn't happen for like x squared, meaning that every pair of different numbers winds up with a different pair of outputs. And we read it like this: if the input u and v are different, then the output fu and fv are different. So this type of function is 1 to 1. And what's important about 1 to 1? 1 to 1 functions have inverse. Okay. So if they go to two different output, then when I reverse it, there will be a function. And here's a function, the picture of a function that is now 1 to 1, like x squared. Okay, so in math course, we draw a lot of these pictures indicating the general conceptual frameworks. Okay, 2x is 1 to 1, and that's easy because two numbers are different, and then twicing them will be different. And the x squared is not 1 to 1 because I have two different x goes to the same number, 9. Okay, if a function is 1 to 1, then the reverse is a function. So can we find out what it is? Well, in general, this problem is very difficult. There's a few examples, we can do this as handout as homework exercise. And probably the ones that are kind of interesting, the only one that kind of interesting are these fractional ones, like these ones, okay? But the linear functions, okay, it's 1 to 1. So how do I solve for the inverse functions? If I tell you y, what is the x? In other words, we solve for x. Okay. So we pretend we know what y is. Y is 7, I put 7 there. And then you solve for x. You clear denominator, divide by 3, then voila. And that's a formula how to get to x, if you tell me what y is. Okay. And we write it like that. Okay, so this is the English procedure. Okay, and we're going to change that formula a little bit later, briefly. Okay. So if I have an inverse pair of formulas, so if f sends A to B, then that means if I use the inverse formula on B, on this side, I will get back to what? Get back to the A. Okay. So you can think of this as code decoding. You send F is like you want to send something, so you code it. And then F inverse is the decoders. Take the coded information, decodes it, become the original information. And back and forth works on both sides in the math case. Okay. And second thing is we have the formulas over here that differentiate the input and output variable x and y, but in general, we use the letter x just as the arguments, what you plug in. So a lot of time we just say, okay, then we just write the inverse formula as a formula in this general dummy variable x. Okay. And so we can talk about these pairs of functions f of x, f inverse of x, since everybody is in general functions of x's. Okay, and then written using this notation, then we have the compositions of, for plugging one into the other, I will recover the original x. So in other words, x will travel a round trick in these pictures. X will go to f of x, then apply f inverse to the f of x output. Then it will bring me back to the original x. Okay, and also this way. If go inverse apply to x, I get to something in the domain or in range in this case, and then goes back to original x. And where's the algebra? Here comes the algebra. So a lot of times we will. So this probably is the most common algebra for play around inverse functions. In algebra, there aren't that many examples you can really calculate. Some basic cubic and these ones. And this one is really a review of some complex fractions. Okay, so it's the practice of fractions. So first we solve for the x. Remember, if I tell you y is 7, then what he said? Well, okay, I solve for x, and then I get all the x on one side, factor the x out, and then divide by the coefficient y. So this is the inverse function. Okay. Depending x. Okay. Now, so we're going to verify that the theorem says f inverse of x should be x. So let's go through the algebra. Meaning what? F inverse of x is all this formula. Okay, and f of x is this formula. And this says take f inverse, put into f. In other words, I'm going to take these and put wherever you see x is, I'm going to replace it by this entire formula, the fractions. What you wind up with is complex fractions. Okay, then you clear the denominator. Okay. And we'll get x. Okay. So this is a common algebra practice. We go through where we go through these types of problems. Okay, so most of the homework problems are these types. See, this is one way, then we can do it the other way. So algebra practice. Okay. Then notice for the case of parabola, if I were to restrict the say 9, say I'm only restrict the function y equal to f of x equal to x squared, where x squared is bigger than positive side. I mean, let's forget about. I only talk about these functions. There's nothing on the left. Then these, then I will know what the answer will give me the output y. Then it is x equal to 3. Okay. In other words, in this case, then f inverse of x does exist, because I know what it is. It is the square root of x. Okay. In other words, f inverse of y, like the square root of y, and the positive square root. So because I know the restrictions of x has to be positive in the beginning. Then in this case, the formula x squared does have an inverse. So that's whether the inverse exists or not depends on the domain, the stretch of the formula you are looking at, the piece of the formula you're looking at. Okay, so that's very important. Okay, and that's a graph of inverse functions. Okay. And if you look at it, it's symmetric. And you say, wait a minute, why is the x squared is inverse symmetric? Well, if you think about it, that's because the coordinates of one becomes the others if we reverse it. Okay. Let's suppose here's f of x, it has an inverse, right? That means That means that when I take the A, when I look at x equal to A, I get y f of A is equal to B, right? Well, what does F inverse does? F inverse does will take B back to A, and so on the graph of F inverse, you have to plot the points BA. And with BA with respect to AB, black points, and I'm going to plot the reverse points BA. Well, that's what equals the diagonal y. Think about it. If I reverse the xy coordinate, I flip the points across the diagonal. X and y are the coordinate are flipped. Okay. So if I plot the entire curve, I get this symmetric mirror image across the diagonal. Okay. Any points on the line y equal to x stays fixed. It doesn't go anywhere during the flip. If the original domain is from A to B, capital A to B, and getting to C to D, and then the flip pictures, the domain will be C to D. Okay, for the inverse formula, and the range it will be the A to B. Okay, the original domain of X, A to B, that becomes the range for the inverse. So here's an example. So in general, if you have to do this really fast, what does the inverse look like? In general, you label the points, a few in the tip of the points and the fixed point, define where they are. And then you plot the reverse, the mirror image of the anchor points. Okay. And that's the mirror image of -1, 3. And that's a mirror image of 3, -3, 2, and that middle point is fixed. And so now you can draw these, and you draw the mirror image. This is like a cusp like that. Okay, that's like a cusp over here. Okay, so that's how we complete the pictures. Okay, and do the homework, and bye bye.